Greetings of the day to all of you. Today we are going to discuss the space vector pulse width modulation approach from the perspective of triangle comparison. I will write here space vector based PWM from the perspective of triangle comparison PWM. Triangle comparison PWM. In our previous class, last class, we have seen that the space vector based pulse width modulation gives the same switching sequence as sine triangle comparison based PWM. For example, for time interval t0, the switching state minus minus minus, that's null vector, minus 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 is applied. This is the switching sequence, okay, and this represents the null vector v0. This is for tz by 2. For time interval t1, switching this vector v1 with the switching sequence plus minus minus is applied across the load. For time interval t2, the switching sequence generated by the inverter, that's the voltage applied across the load, is plus plus minus. This is the sequence, okay. Then for another tz by 2, null vector v7 is applied across the load, which has the switching sequence of plus plus plus. That completes one subcycle, ts, which is equivalent to half of the carrier cycle, okay. And other half of the carrier cycle will apply the same switching sequences but in reverse order. That means for tz by 2 time, switching sequence plus 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 will be applied, okay. For t2 time interval, switching sequence plus plus minus will be applied. For time interval t1, switching sequence plus minus minus will be applied, and for tz by 2 interval, switching sequence v0, that's minus minus minus, will be applied. That completes other subcycle, okay. So you have seen that we had taken a triangular carrier wave, one wave of the one triangular carrier wave with period as ts and ts, which is called subcycle. This is half of the carrier cycle with period ts, and other half of the carrier cycle also has period ts. In first subcycle, that is from here to here, we compare actually three sinusoidal modulating signals, mr, my, and mb, with this carrier wave, and it gives this switching sequence. I mean, for time interval tz by 2, it at its output gives the switching sequence minus minus minus, then for t1 plus minus minus, and so on in one subcycle. In subsequent subcycle, it gives the same switching sequence but in reverse order. And this is if you consider sine triangle modulation, sine triangle comparison PWM. But same switching sequences generated if you don't use sine triangle comparison method, if you use space vector based approach. In space vector based approach also, this is the switching sequence which is generated by the inverter in two subcycles, ts and ts. That is, this is one sample time, and during this sample time it generates the reference vector vref. In next sample time, it again repeats the same switching sequence, and that would have rotated your reference vector by an angle alpha, and so on, okay. Depending upon how many what is the switching frequency, you will have a large number of samples, okay, and hence a rotating reference vector will be created. This rotating reference vector will basically represents these switching sequences, and of course it represents a set of three-phase sinusoidal phase voltages and a set of three-phase sinusoidal line voltages. Then what is the difference between sine triangle comparison based PWM and space vector based PWM? If same switching sequences generated, say in sector 1 by both of them. This switching sequence is for sector 1 from space vector PWM modulation based approach. Okay. The difference being the null vectors Tz by 2 and Tz by 2 are not equal in sine triangle comparison. Let me call this time interval Tz by 2 T0 and let me call this time interval as T7. In sine triangle PWM, in sine triangle comparison based PWM, T0 is not equal to T7. The time intervals for two null vectors is not equal in each subcycle. So that makes that gives rise to large harmonic, slightly larger harmonic distortion in the inverter output voltage, and in the load current, the ripple in the load current will be higher. Whereas in space vector PWM technique, same switching sequences, followed by space vector approach also, say in sector 1, similarly in other sectors. But in space vector based PWM technique, SVPWM technique, the time intervals for two null vectors is same. That means that two null vectors are equally divided. T0 is equal to T7. The time interval for which this null vector V0 with switching sequence V minus 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 is exactly equal to time interval for which the other null vector V7 with switching sequence plus 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 is applied. The two time intervals are same, which gives less harmonic distortion in inverter output voltage and less current ripple in the load current. And when we compare space vector PWM with sine triangle PWM, although they generate same switching sequence, but the null times are not equal. So the comparison tells us that space vector PWM produces about 15.5% higher inverter output voltage, AC voltage, than sine triangle PWM. That's number one. And number two, the T0 is equal to T7 in SVPWM technique, whereas T0 is not equal to T7 in sine triangle PWM. So therefore, the harmonic distortion is less in space vector PWM technique than in sine triangle PWM technique. If you remember, in one of the classes we discussed about third harmonic injection PWM. In third harmonic injection PWM, I will write here third harmonic injection PWM. If you remember, a common mode third harmonic signal was added to sinusoidal modulating waves, and that modulated our reference waves, something like this, three reference waves, MR star, MY star and MB star. Okay, and then we had two optimal values. For K equal to 1 by 6, the inverter produced 15.5% higher output voltage than sine triangle PWM. And for K equal to 1 by 4, it produced less minimum harmonic distortion. But it was not possible using third harmonic injection PWM to achieve both the objectives. That is, to have inverter output voltage 15.5% higher and simultaneously less harmonic distortion. However, in space vector PWM technique, both these both the objectives are achieved. Space vector based PWM technique is equivalent to K equal to 1 by 6 as well as K equal to 1 by 4 when you compare it with third harmonic injection PWM. That means space vector PWM technique produces 15.5% higher inverter output voltage and simultaneously less harmonic distortion, which was not possible with third harmonic injection PWM technique. In third harmonic injection PWM technique, only one objective could be fulfilled at a time, either for K equal to 1 by 6 or for K equal to 1 by 4. But space vector modulation, it combines the best features of third harmonic injection PWM. That means it produces the AC three-phase AC output voltage at the output of the inverter with about 15.5% higher value as well as least harmonic distortion. Okay, and this is not possible with sine triangle PWM. Sine triangle PWM neither produces 15.5% higher inverter output voltage, nor does it produce, nor does it give least harmonic distortion. Right. Now from let me draw again space vector based approach. Say this is time interval t naught. This is time interval t naught, right? This is time interval t1. This is dwell time t2. This is dwell time t7. And then this completes one subcycle ts, and then we have another subcycle where we will start with ts, it's t7 itself, t7, then reverse order t2 will t2 dash, let's call this t7 dash, t2 dash, t1 dash, and t naught dash. Right. So the switching sequence which is applied in t naught time is minus minus minus. This the switching sequence is like this. V naught voltage space vector is applied first, then V1 voltage space vector, then V2 voltage space vector, then null vector V7 in one subcycle. This is in one subcycle. Then in other subcycle, this reverse order is applied. V7 first, followed by V2 voltage space vector, followed by voltage space vector V1, followed by voltage space vector V0. Another subcycle, right? Okay, so V0 means switching sequence minus minus minus. It's applied across the load for dwell time or null time where T0. For dwell time T1, the switching sequence is plus minus minus. For T2, voltage space vector V2 is applied, which has a switching sequence of plus plus minus. For T7, null vector V7 is applied, which has a switching sequence of plus plus plus. Then in reverse order, plus plus plus, then plus plus minus, then plus minus minus, then minus minus minus. That's it. Okay, so it gives us pole voltages. For example, if you plot pole voltage VRO, this VRO will say, for example, this is omega t axis for VRO. In first time interval T0, minus means phase leg or bottom switch is on, so it gives the pole voltage equal to minus VDC by 2. Then for 1, 2, 3, 4, 5, 6 time intervals is plus all the way, means top switch is on and pole voltage VRO is plus VDC by 2. Okay, up to this, and then it is minus VDC by 2 again. This is pole voltage VRO. What about pole voltage VYO? Pole voltage VYO we can draw here. Is minus the phase leg B has status switching sequence of minus minus for 2 intervals. Means bottom switch is on, and for 2 intervals the pole voltage is minus VDC by 2. Then for 1, 2, 3, 4 intervals is plus VDC by 2. 1, 2, 3, 4. Then it is again minus VDC by 2. Similarly, you can draw pole voltage VBO. Okay, VBO we can draw here. VBO, it is minus 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 for 3 intervals. Bottom switch of phase leg B is on, so it gives pole voltage minus VDC by 2. Minus 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 up to this, minus VDC by 2. Then for 2 intervals T7 and T7 dash plus plus, so pole voltage is plus VDC by 2. And then again for 3 time intervals minus VDC by 2. This is space vector based approach. In space vector based approach in sector 1, and this switching sequence is valid for sector 1. In sector 1, this is the switch sequence. Your reference vector is produced, and your one sample time comprises of T0, T1, T2, T7, then T7 dash, T2 dash, T1 dash, T0 dash, and this completes one sample, and it produces the reference vector VREF, and this reference vector represents 3 phase voltages, like 3 phase pole voltages VRO, VYO, VBO, from which we can find 3 line voltages VRY, VYB, VBR, and 3 phase voltages VRN, VYN, and VBN. Each voltage space vector basically represents 3 phase voltages. Okay, this is in sector 1. So this is the space vector approach. So in space vector approach, what will your processor do? It will find the sector and it will find the nearest three vectors. The nearest three vectors are V0, V1 and V2. And for time interval T0, it will apply voltage space vector V0. For time interval T1, it will apply voltage space vector V1. For time interval T2, it will apply voltage space vector V2. For time interval T7, it will apply voltage space vector V7 in one subcycle and in reverse order in another subcycle. That means it will generate the control pulses or gating pulses for inverter switches as per these switching sequences, so that your pole voltages VRO, VYO and VBO at any instant of time are like this. And then inverter produces three-phase line voltages VRY, VYB, VBR and three-phase voltages VRN, VYN and VBN in sector 1. In each sample, the sequence is like this. So this is space vector approach. The question, and in this space vector approach, you can see in one subcycle, time interval T0 for null vector V0 is exactly equal to time interval T7 for null vector V7. We have two null vectors, V0, which represents the switching sequence minus, 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 and V7, which represents the switching sequence plus, plus, plus. V0 is applied for time interval T0, and this T0 and V7 is applied for time interval T7. And you can see in space vector approach, T0 is exactly equal to T7. Similarly, T0 dash is equal to T7 dash in next subcycle. So in all samples, in all subcycles, you will see that these dwell times are always equal. T0 is equal to T7 or T0 dash is equal to T7 dash. This is true with space vector based approach. Whereas in sine triangle approach, sine triangle comparison based approach, that will also give same switching sequence. But in that case, T0 will not be equal to T7 and T0 dash will not be equal to T7 dash. The question is, can we use triangle comparison where we can have a modulating wave in such a way that it also produces same switching sequence as space vector based approach, and simultaneously it gives us equal dwell times for null vectors. That means it gives T0 is equal to T7 and T0 dash is equal to T7 dash. Is it possible? The answer is yes, it is possible. If our modulating reference waves are not sine waves, they are some other waves. If you generate a common mode signal, add to three sinusoidal modulating waves, and then your three modulating sinusoidal waves get modified to modified modulating waves, and those modulating waves, when compared with high frequency triangular carrier wave, will produce the same switching sequence, the same type of pole voltages, and simultaneously it will make the time intervals for null vectors equal to same. That is T0 equal to T7 or T0 dash equal to T7 dash. Okay. For that purpose, the question is, what type of modulating signal will that be? Modified modulating signal. It cannot be third harmonic injected. In third harmonic injection PWM, we had a third harmonic, common mode signal like this. We found that gives us either for k equal to 1 by 6 higher inverter output voltage, or for k equal to 1 by 4 least harmonic distortion, but it does not give both of them. Okay. It cannot be any, what will be the nature of this modulating wave? We will try to find out that in a minute's time. Now you can see here from here that this pole voltage VRO is positive for most of the time, and it is negative for very small interval of time, so that your modified modulating wave is here it is, let us call this MR dash, and this MR dash is exactly equal to average value of pole voltage VRO. So this is for example, this is your pole voltage VRO, and its average is as given by this dashed line. And this MR dash is basically, it is scaled version of VRO. Scaled version of pole voltage VRO. We have already discussed it in one of the previous classes. I told you that the modulating waves are scaled versions of your pole voltages. So the average pole voltage is like this, and let us call this modified modulating wave MR dash. Let us come to VYO pole voltage. VYO pole voltage is like this. So here, what will be the average pole voltage. So average pole voltage here will be almost equal to 0. Let me show that by a dashed line like this. This is the average pole voltage, and this will be your my dash, because my dash is also my star, sorry, not dash. My star is also scaled version of pole voltage VYO. It's nearly equal to 0, because if you find average value of this pole voltage VYO, it is very nearly equal to 0. And what about VBO, average pole voltage VBO? It is negative for most of the time, so its average value will be minus. And MB star will be the scaled version of this average pole voltage VBO, scaled version of it. So therefore, if we have three modified modulating waves, MR dash, MY dash, and MB dash, and compare them with a common high frequency triangular carrier wave like this. This is our high frequency triangular carrier wave. I will compare with high frequency triangular carrier wave like this. So start from here, यहाँ तक, and then like this. Okay. Similarly, this will be compared with triangular carrier wave like this. Same triangular carrier wave, and this will also be compared with same triangular carrier wave like this. So we have triangular carrier wave. It's not, we don't have three triangular carrier waves. We have same triangular carrier wave, and this triangular carrier wave is compared with MR dash. We can see from this instant to this instant, triangular carrier wave is higher in amplitude than modified modulating wave MR dash. So bottom switch of phase leg R is on, and VRO is minus VDC by 2. Then from this instant to this instant, you can see, MR dash is higher in amplitude than triangular carrier wave, and top switch is on, and VRO is plus VDC by 2. Then here it's again minus VDC by 2. Same is case with VYO, and same is case with VBO. For example, in VBO, from this instant to this instant, you can see triangular carrier wave is higher in amplitude than MB dash. So bottom switch of phase leg B is on, and VBO is minus VDC by 2. From this instant to this instant, MB star is greater in amplitude than triangular carrier wave. Top switch of phase leg B is on, and VBO is plus VDC by 2. Then from this instant to this instant, again triangular carrier wave is higher in amplitude than modified modulating wave MB star, and bottom switch is again on, and VBO is minus VDC by 2. So therefore, the space vector based PWM approach, when we study it from the perspective of triangle comparison PWM, it tells us that it is possible to generate the same switching sequence as generated by space vector based PWM. Say for example, this is the switching sequence in sector 1, and simultaneously it is also possible to make T0 equal to T7, the null vector times equally distribute them equally between V0 and V7, or to make null vector dual times equal. If our modulating waves are not sinusoidal modulating waves, they are modified modulating waves, MR dash, MY dash, MR star, MY star, and MB star. The question is, what will be the nature of these modified modulating waves, which will produce same results as produced by space vector PWM? Okay, because we have seen sine triangle comparison PWM does not produce same results as space vector based PWM. There T0 is not equal to T7, and it does not give 15.5% higher inverter output voltage. However, if we are able to modify our modulating waves, instead of having sinusoidal modulating waves MR, MY, and MB, if we have modified modulating waves MR star, MY star, and MB star, we can have same switching sequence, say for example in sector 1, as that produced by space vector based approach, and we can also make T0 equal to T7. So then the triangle comparison PWM will be exactly same as space vector PWM approach. It will produce same output. So therefore it is possible. Now the question is, what will be the nature of those modified modulating waves? We have to find that. Before that, you must remember that the sum of the pole voltage is VRO plus VYO plus VBO. It's not equal to 0. And similarly, the sum of the three modulating waves, MR star plus MY star plus MB star, it is also not equal to 0 if your modulating waves are sinusoidal, say MR, MY and MB, as in sine triangle PWM, which we have studied in last class. Then in that case, the three sinusoidal waves are balanced waves, their sum is equal to 0. But when you are modifying your modulating waves, they are not sinusoidal, you are adding some common mode signal to them. They become MR star, MY star, MB star, and then their sum is not equal to 0. In fact, their sum is 3 times the common mode signal. So MR star plus MY star plus MB star, it is equal to 3 times the common mode signal, MCM. Because what is your MR star, modified modulating wave for phase leg R? It is original sinusoidal modulating wave plus common mode signal, MCM. What will be the nature of this common mode signal? We will find that in a minute's time. Similarly, the modified modulating wave, MY star, is original modulating sinusoidal modulating wave, MY, plus common mode, same common mode signal, MCM. And MB star is original sinusoidal modulating wave, MB, plus common mode signal, MCM. And when you add them up, MR plus MY plus MB is 0, but MCM plus MCM is 3 MCM. So MR star plus MY star plus MB star is not equal to 0, but this sum is equal to 3 times MCM. Okay, fine. Now if you find average, pole voltage VRO from these waveforms, VRO average. Now this VRO average is equal to, either it is plus VDC by 2 or it is minus VDC by 2. It is plus VDC by 2 for this time interval, T1, T2, T7 in one subcycle. So it is equal to VDC by 2 in one, let us take one subcycle only, this. In this subcycle, it is plus VDC by 2 for time interval T1 plus T2 plus T7. So I will write plus VDC by 2 in how much time? In T1 plus T2 plus T7, right? And it is equal to minus VDC by 2 in one time interval, that's T0. It is minus VDC by 2 into T0. Now since this triangle comparison based PWM is exactly equivalent to space vector approach, so T0 is exactly equal to T7. So this minus VDC by 2 T0 will cancel with plus VDC by 2 into T7. So your average pole voltage VRO average will be then equal to VDC by 2 times T1 plus T2 only, because VDC by 2 into VDC by 2 into T7 is exactly equal to minus VD is exactly equal to VDC by 2 into T0, because if T0 is equal to T7, they cancel out. And in terms of modulating wave, it is equal to MR star by VP into VDC by 2, okay, or it is equal to VDC by 2 VP into MR star. So that means this MR star is a scaled version of average pole voltage VRO. So it is VDC by 2 VP into MR star. This is average pole voltage of phase leg R, that's VRO. What about VYO, average pole voltage? Now you can see VYO, it's positive, it is equal to plus VDC by 2 for how much time? It is in one subcycle for time interval T2 plus T7. T2 plus T7 minus, and it is minus VDC by 2 for time interval T0 and T1. Minus VDC by 2 T0 plus T1. Again, T0 is equal to exactly T7, and you will get VRO average equal to VDC by 2. So effectively it will be equal to VDC by 2 into T2 minus VDC by 2 into T1, and it is equal to VDC by 2 VP in terms of modulating wave into MY star, right? And similarly, your third average pole voltage VBO average is equal to, you can see this VBO average in one subcycle is positive, it's plus VDC by 2 in only one time interval, that is T7. And then for 1, 2, 3, three time intervals, T0, T1, T2, it is minus VDC by 2. Minus VDC by 2 for time intervals T0 plus T1 plus T2. Now this T0 is exactly equal to T7, so it is equal to effectively minus, so this term cancels with this term, it is minus VDC by 2 into T1 plus T2. And in terms of modulating wave, modified modulating wave, it is VDC by 2Vp into MB star. So this MB star is scaled version of this pole voltage. Okay, so therefore we have come to the conclusion that it is possible for us to produce exactly the same switching sequence, same results, and make the null vector times exactly equal to T0 equal to T7 in each subcycle with triangle comparison based PWM if our modulating waves are modified. They are not MR, MY, MB. They are some modified modulating waves, MR star, MY star, MB star, where MR star is MR plus MCM, MY star is MY plus MCM, MB star is MB plus MCM. Now the question is, what will be this common mode signal? What will be the nature of this common mode signal? Let us try to find out this common mode signal. Now this common mode signal should be in such a way that it divides the null vector times equally. Okay. So we will now have triangle comparison based. I'm not writing sine triangle comparison because our modulating waves are not sine waves now. They are modified modulating waves. They are non-sinusoidal. So I'm writing triangle comparison. Triangle comparison based PWM with division of equal null vector time. Or I can write it like this: division of equal null vector time, division of equal null vector time using triangle comparison based PWM, using triangle comparison PWM. We know in space vector PWM, null vector times are equal. Okay, the division is there equal. Can we have equal division of null vector times with triangle comparison? Yes. If we modify our modulating waves, if we add common mode signal and modify our modulating waves, we are going to discuss that division of equal null vector time, that is making T0 equal to T7, not by space vector PWM, because space vector PWM by default makes T0 equal to T7. We are going to now discuss division of equal null vector time, that is T0 equal to T7, using triangle comparison PWM. Okay. Now using triangle comparison PWM, let us assume, let the three original modulating waves, let the three original sinusoidal modulating waves, because original modulating waves are sinusoidal modulating waves. Let the three original sinusoidal modulating waves be MR, MY and MB, or I can write M max, M mid and M min. You have to understand this. So you can understand it if you draw the modified modulating waves like this. This is my modified modulating wave, MR. Sorry, not modified modulating wave, original modulating wave, sinusoidal modulating wave, MR. This is my original modulating wave for phase leg B, MY, phase leg Y, MY. And this is the original sinusoidal modulating wave for phase leg B, that is MB. At any instant of time, now for example, which modulating wave is there? This is MB, this is MR and this is MY. At any instant of time, you can divide these modulating waves into positive maximum value, negative minimum, or maximum value, minimum value and middle value. For example, during this 30-degree interval, यहाँ से यहाँ तक, MB is positive, so I can call it M max, okay? My is negative, I call this my as m min, and बीच वाली waveform कौन सी है, which is between maximum and minimum, mr, so mr is m mid. इसी तरह अगर आप ये 30 डिग्री इंटरवल लेंगे, यहाँ से यहाँ तक, से यहाँ से यहाँ तक, इसमें mr is again, mr is, you know, yeah, let us take from this instant to this instant, यहाँ से यहाँ तक. From this instant to this instant, my is now m max, mb is m min, and mr is m mid. So at any instant of time, okay, you will have three modulating waves, out of which one will be having maximum value means positive value, another will be having minimum value, less value, maybe negative, and the third one will be having, it will be in between the two, mid, m max, m min, and m mid. And if you try to study it from space vector point of view, okay, in space vector PWM technique, if you, for example, in sector 1, mr is equal to m mid. In sector 2, m mid will be now different wave, mb is equal to m mid. And in sector 3, in sector 2, my is m mid. And in sector 3, there is some mistake here. In sector 1, my is equal to m mid. In sector 2, mr is equal to m mid. And in sector 3, mb is equal to m mid. Please make corrections. I repeat, in sector 1, my is equal to m mid. In sector 2, mr is m mid. And in sector 3, mb is m mid. How do I know it? I had given you yesterday when we had drawn that space vector hexagon. I told you, where from a particular phase voltage starts. Okay, it completes positive half cycle and negative half cycle for all the three phase voltages, Vrn, Vyn, and Vbn. And you know in each sector which voltage waveform is positive, which is negative, which is more positive, which is more negative. From that you can find in each sector which waveform is having middle value. In sector 1, my is having middle value m mid. In sector 2, mr is equal to m mid. And in sector 3, mb is equal to m mid. Similarly, you can find in other sectors. Fine. Now, m max, what we are going to do, we are now having three sinusoidal modulating waves. Instead of calling them mr, my, m mid, I call them m max, m mid, and m min. Okay, this may be mr, this may be my, this may be mb, or this may be mb, this may be mr, this may be my. It depends upon in which sector you are, at which instant you are trying to determine. In general, we will call the three modulating waves sinusoidal original modulating waves: m max, m mid, and m min. Now, if we want equal division of null vector times, we want T0 exactly equal to T7. Division of null vector times equally, T0 equal to T7. I have to modify these original sinusoidal modulating waves. I have to add common mode signal in all of them, and they will get modified like this. So I will write here modified modulating waves. Modified modulating waves are, that is for T0 equal to T7, for equal division of null vector times, the modulating waves get modified, and the modified modulating waves are m max star. M max star is original sinusoidal modulating wave, m max, plus some common mode signal, MCM, right? Similarly, second modified modulating wave is m mid star. It is equal to original sinusoidal modulating wave, m mid, plus some common mode signal, same common mode signal, MCM. And similarly, third modified modulating signal, m min star, is equal to original sinusoidal modulating wave, m min, plus common mode signal, MCM. Right? Now we know that m max plus m mid plus m min these three sinusoidal modulating waves, their sum is equal to 0. But the sum of modified modulating waves, M max star plus M mid star plus M min star, this sum is not equal to 0. It's not equal to 0. We already know. I have discussed it a few moments back. And then for equal null vector times, if you want that T0 should be exactly equal to T7, as in case of space vector PWM, the condition is that M max star should be equal to minus M min star. This is the mathematical condition for that. If you want that T0 should be exactly equal to T7, that is the null vector times should be same, they should be equal, then M max star should be equal to minus M min star, which means M max star, take this M min star to left hand side, it becomes plus M min star is equal to 0. Now what is our M max star? We already know that our M max star is M max plus MCM. So I will write M max star equal to M max plus MCM plus M min star. M min star is M min plus MCM. So it is M min plus MCM is equal to 0. So that gives me M max plus M min plus MCM is 2 MCM equal to 0. Now we know that the sum of three original sinusoidal modulating waves, M max plus M mid plus M min, we know this is equal to 0, their sum is 0. From this we can find M max plus M min. So M max plus M min is equal to, take it to right hand side, it is minus M mid. So substitute it in this equation. So M max plus M min is minus M mid. Okay, so therefore our equation becomes, this is M max plus M min. M max plus M min is minus M mid. So minus M mid plus M 2 times MCM is equal to 0, right? Or 2 times MCM is equal to, take it to right hand side, it will become plus M mid. That will give us common mode signal MCM equal to M mid by 2, that is 0.5 M mid. So this gives us an idea of how to calculate MCM, common mode signal. So what you have to do, you have to draw three original sinusoidal modulating waves, and then you have to take the middle value after each 30-degree interval, and you have to take half of that, and that will be your common mode signal. Add that common mode signal to three original sinusoidal modulating waves, M max, M min and M mid. That will give modified modulating waves, M max star, M min star and M mid star, and compare those three modulating waves with high frequency triangular carrier wave, generate the control pulses for 6 switches of the inverter, and you will get same results as given by space vector PWM. Your inverter output voltage will increase by about 15.5%, and T0 will be equal to T7, null vector times will be equal, it will give least harmonic distortion in the voltage. Same results as produced by conventional space vector PWM. So let me see how we can generate this common mode signal MCM. So I will write this common mode signal again here, MCM is equal to 0.5 M mid. So let us try to find it out. For that purpose, let us draw the waveforms for three original modulating waves. Our three original modulating waves are like this. This is one modulating wave. After 120 degrees, we get another modulating wave, sinusoidal modulating wave. After another 120 degrees, we get the third sinusoidal modulating wave, like this. So these are our three original sinusoidal modulating waves. Say MR, MY, MB, or M max, M min, M mid. Now this is 0 degree here and ये कितना degree है? This is 30 degrees. So 0 to 30 degrees, you have to see, let us call this original modulating wave MR, this is MY and this is MB. These are three original sinusoidal modulating waves as we already know. Now from 0 to 30 degrees, how do you find common mode signal? Your common mode signal is 0.5 M mid. I will draw that separately. I will draw waveform for common mode signal, MCM. So this is 0, this is 30 degrees. From 0 to 30 degrees, this is the mid. See, this is M max is MB, this is M min is MY. And what is M mid? Middle कौन सी है इन तीनों waveforms में? MR is middle. MR is the M mid. It's between M max and M min. So that means from 0 to 30 degrees, I will draw this MR. MR is my middle waveform. And at this point, what is its value? Say it is sinusoidal waveforms. Here angle is 30 degrees and sine 30 degrees is 0.5. That means इसका peak value 0.5 है. Here it is 0.5. And this angle is 30 degrees. Right? Then go from 30 to 60 degrees. Here is 60 degrees. From 30 to 60 degrees, which waveform is middle, M mid? MR is now your M max. यहाँ से यहाँ तक देख लीजिए. MR is M max. You can see MY is M min. Okay, MY is M min. And which waveform is M mid? यहाँ से यहाँ तक देख लीजिए. यही waveform M mid है. ये waveform M mid है. MB is M mid. I repeat, from 30 degrees to 60 degrees. This is your M max. MR is M max. This is M min. MY is M min. और ये आपकी M mid है. और M mid क्या है? M mid MB है. This basically is MB. MB is your M mid. ये 60 degree तक है. Okay, I will go up to 60 degrees. मैं इसको थोड़ा zoom करके draw कर रहा हूँ. 60 degrees. 60 degrees से 90 degree तक. This is 90 degree. MB is still M mid because you know MR is still M max. And you know MY is still M min और MB आपका M mid अभी भी है 60 से 90 degrees तक. ये 60 से 90 degrees तक ये है आपका 90 degrees. It's MB. MB is your M mid. So from 0 to 30 degrees, MR is M mid. From 30 to 60 and 60 to 90 degrees, MB is M mid. So you can see MB is M mid here and MB during this interval is also M mid. अब आगे चलिए 90 to 120 degrees, 90 से 120 degree तक MR is M max, MB अब M min बन जाती है और बीच वाली कौन सी बनती है? बीच वाली ये बनती है MY. So 90 to 120 degrees तक ये आपकी बनती है MY is M mid. So 90 to 120 degrees. MY is now M mid. और 120 से 150 degrees तक MY it remains M mid. 120 to 150 degree it remains M mid. ये M mid ही रहती है. ये आपका 150 degrees है. MY remains M mid. So I am here now. उसके बाद चलिए आगे चलते हैं. 150 से 180 degrees तक which waveform is middle? ये देखिए ये मैक्स है, ये मिन है और ये मिडल है. एम आर फिर से एम मिड बन जाती है 180 डिग्री तक. 180 डिग्रीज तक एम आर फिर से एम मिड बन जाती है. और 180 डिग्रीज टू 210 डिग्रीज इट इज स्टिल एम आर विच इज एम मिड. ये 210 डिग्रीज है, स्टिल रिमेन्स एम मिड यहाँ तक. Now 210 degrees to 240 degrees, which waveform is M mid? MB is now M mid. 210 to 240 degrees, MB is M mid, and you can continue like that. This is how you find the M mid. But what is your MCM? Your MCM is not M mid, it is 0.5 times M mid. तो आप इसका 0.5 ले लीजिए, आधा कर लीजिए. इसका पीक वैल्यू है 0.5 है और 0.25 समवेयर यहाँ होगा, ये 0.25 इसका आधा होगा 0.25। सो ये मेरी 0.5 एमिड है, 0.5 एमिड, 0.5 एमिड, 0.5 एमिड। दिस इज हाउ आई फाइंड, और ये मेरी MCM बन जाती है। सो MCM इज 0.5 एमिड, इट इज 0.5 MR 0 to 30 degrees, 0.5 MB 30 to 60 degrees, 0.5 MB again 60 to 90 degrees, from 90 to 120 degrees it is 0.5 MY, from 120 to 150 degrees it is still 0.5 MY, ये इसका आधा है, from 150 to 180 degrees ये MR है, इसका आधा 0.5 MR है, and so on. So this is how we generate common mode signal. And once you have generated the common mode signal, so you just add that common mode signal to all the three sinusoidal modulating waves, and that will modify your modulating waves. Your modulating waves will become MR star, MY star, MB star, and compare those modified modulating waves with a common high frequency triangular carrier wave and generate the control pulses or gating pulses for inverter switches. So let me show you that. So I will draw MR first, original modulating waves, MR, MY and NB. This is original modulating wave, MR, and let me take its peak value equal to 1.154, not 1, but 1.154. 1 is somewhere here, ये 1 है. This is modulation index 1, this is 1.154. Okay, similarly negative half cycle में this is minus 1.154 and this is minus 1. This is minus 1.0. This is MR. MY will start after 120 degrees, say somewhere here. This is my MY, original modulating wave. MY. And original modulating, sinusoidal modulating wave, third is MB, after another 120 degrees, MB. This is original modulating, sinusoidal modulating wave, MB. Now in these original sinusoidal modulating waves, MR, MY, MB, you have to add common mode signal. And what is common mode signal? That's 0.5 mid. And just few moments back we found 0.5 mid from 0 to 30 degrees. M mid is MR. MR इतना है, इसका आधा ये है. So 0.5 M mid ये है. From 30 to 60 degrees, it's again 0.5 M mid. ये 0.5 MR है और ये 0.5 MB है. From 60 to 90 degrees, it is again 0.5 MB आधा. From 90 to 120 degrees, it's 0.5 MY है, क्योंकि MY middle है. So it's not MY, it is 0.5 MY. So it's 0.5 M mid. From 120 to 150 degrees, it's 0.5 MY again. It's not MY, इसका आधा है 0.5, because your MCM is not M mid, it is 0.5 M mid. From 150 to 180 degrees, it's again 0.5 MR, so it will come down. Then from 180 to 210 degrees, it's again 0.5 MR. From 210 degrees to 240 degrees, ये बीच की सिग्नल है, M mid है, MB, so इसका 0.5 ये है, that's 0.5 M mid, 0.5 MB, that's 0.5 M mid, and then for next 30 degrees, it's same 0.5 M mid, so you can continue like this. तो ये आपकी M mid है. This is your MCM. This is your common mode signal. Now you can see this common mode signal, third harmonic injection में common mode signal कैसी होती थी. it was third harmonic sinusoidal wave like this. It's not like that. It is a sort of triangular carrier wave. Sorry, not carrier, sort of triangular wave, something like this. Although यहाँ से यहाँ तक ये sinusoidally vary होती है, it's not a straight line, exactly straight line. It's basically 0.5 mr. mr चूंकि sinusoidally vary होता है, ये भी sinusoidally vary होती है, but it looks like a straight line. So it gives a sort of triangular wave. So ये आपकी common mode signal बन जाती है. Now what is the rule? Your original modulating wave mr star now becomes mr plus mcm. Similarly, the modified modulating wave, modified modulating wave mr star is equal to mr original modulating wave mr plus mcm. Modified modulating wave my star is original sinusoidal modulating wave my plus mcm, and modified modulating wave mb star is equal to original sinusoidal modulating wave mb plus mcm. Use this rule, which we have used it a number of times in module number 3 when we were discussing triangle comparison based PWM techniques. mr plus mcm, यह आपका mr है, इसमें mcm आप ये common mode signal है जो हमने अभी derive की, ये ऐड कर लीजिए. So it becomes maximum somewhere here. So mr increase हो रहा है, mcm भी increase हो रहा है, and it goes to maximum value somewhere here. तो यहाँ ये maximum value achieve करेगा, but it will not go beyond 1. Although your original modulating wave is over modulated, it is 1, its peak value is 1.154. This will not go beyond 1. ये 1 पे आ जाएगा. उसके बाद ये decrease हो जाएगी. For example, at this instant of time, you can see at this instant of time, your MCM is 0, and your original modified modulating wave MR star is MR plus MCM. तो MR ये है, MCM 0 है, तो ये it means it will come down. ये वापस इधर आएगी. So come down like this. उसके बाद यहाँ से यहाँ तक your MCM becomes negative, and MR is no doubt positive. So MR में से MCM अब subtract हो जाएगा. यहाँ से यहाँ तक add होता था और यहाँ subtract हो जाएगा. And when it subtracts at this peak of the MCM, it will have minimum value. Minimum value. So इसका head नीचे जाएगा. Its head will go down. Then at this instant of time, it is again MR plus MCM. MR इतना है, MCM 0 है, तो ये वापस इधर जाएगा. Okay, and it will achieve peak value again near the peak of MCM. So peak means it will go to unity value. Okay, उसके बाद आप continue कर लीजिए. You continue it. This instant, this instant, this instant. So it will again go down. It will have minimum value here, and then it will go up again, and it will have maximum value here. I'm sorry. इसके बाद तो ये negative जाएगा. Sorry, it will go to negative. ये negative half cycle अब complete करेगा. It will not go here. It will अब इसके बाद ये negative है, negative की तरफ जाएगा. It will go negative. और यहाँ पे ये negative peak achieve करेगा. और यहाँ पे so this is your MR star. Modified modulating wave MR star. What about MY star? MY star यहाँ से शुरू होगा. It will start from here and it will achieve peak value somewhere here. तो इसका peak value यहाँ पे ही होगा जहाँ पे इसका peak value. Then it will come down here. ये यहाँ आ जाएगा and it will have minimum value here. Its head will go down. Then it will go up again. It will cross this and it will have another peak here. Okay. Then it will go through the negative half cycle like this, and previously also it will have some negative half cycle like this. So this is my MY star. What about MB star? MB star will start from here, MB plus MCM. So it will achieve peak value somewhere here, and then यहाँ पे MCM 0 है, so it will come down. and here it will have its head will go down, it will have minimum value here, then again go up, it will have peak value somewhere here like this. Similarly in the negative half cycle like this, you can continue this way, something like this. So this is my MB star. Fine. So therefore our modified modulating waves are not sinusoidal now. Our modified modulating waves are MR star, which is original sinusoidal modulating wave MR plus common mode signal MCM. MY star is this, it's also MY plus MCM, and MB star is this, it is MB plus MCM. And how did we generate this MCM? What was the condition for this MCM? If you remember a few moments back, I told you that condition for this MCM is that this MCM comes out to be equal to 0.5 M mid. That's how we generate. And how did we get this? We distributed null vector times equally. We made T0 exactly equal to T7. When we made T0 exactly equal to T7, we derived the equation and we got this equation, and our MCM was found out to be 0.5 M mid. And for common mode signal, we calculate like this, 0.5 M mid, as we have calculated here. It will give modified modulating waves, and when these modified modulating waves MR star, MY star, MB star are compared with a common high frequency triangular carrier wave like this triangular carrier wave, we get gating pulses for inverter switches, and inverter produces output voltage, three-phase output voltages, three-phase line-to-line voltages, three-phase phase-to neutral voltages, whose instantaneous average value will be sinusoidal, because I told you, although your pole voltages are scaled version of your modified modulating waves, your pole voltages will look like exactly same as MR star, MY star, MB star. Like for example, your pole voltage VRO will have same shape as MR star, distorted. VYO will have same shape as MY star, and VBO will be similar to MB star, scaled versions. But in line-to-line voltages and phase voltages, common mode signals do not appear there, and your line-to-line voltages and phase voltages, which are actually the voltages impressed across the three-phase load, they will be purely sinusoidal. The instantaneous average value of those voltages will be sinusoidal, with the advantage that T0 will exactly be equal to T7. And if you take sector 1 of space vector PWM, and here also you can see, you take just one carrier cycle. In one carrier cycle, you will see that these are the voltage space vectors which are getting applied across the load. V0 with switching sequence minus minus minus, it will get applied across the load for time interval T0, followed by V1 voltage space vector with switching sequence plus minus minus, it will get applied across the load for dwell time T1. V2 with switching sequence plus plus minus, it will get applied across the load for dwell time T2. Null vector V7 with switching sequence plus plus plus, it will get applied across the load for time interval T7, and that completes one subcycle. And in this subcycle, you will find that T0 will be exactly equal to T7, similar to space vector PWM. Whereas it was not the case in sine triangle PWM. In sine triangle PWM also we had the same switching sequence, but T0 was not equal to T7. This is one but in this triangle comparison based PWM technique, where we generated the common mode signal using this equation, MCM equal to 0.5 M mid, and the modified modulating waves gave rise to T0 equal to T7. Same switching sequence as in sine triangle PWM or as in space vector based PWM, but with T0 equal to T7, which is also the case with space vector based PWM, but it's not the case with sine triangle PWM. This is one subcycle. In another subcycle, the reverse switching sequence will be there. V7 null vector will be applied first, plus plus plus, followed by V2 vector, active vector, plus plus minus. For this will be for T7 dash, this will be for T2 dash, followed by active voltage space vector plus minus minus V1 for time interval T1 dash, followed by null voltage vector V0 minus 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 for time interval T0 dash. That completes second subcycle, and ये एक sample आपका complete हो जाता है. That's it. So therefore, we can say that space vector PWM technique that gives this switching sequence in a particular sector, that's sector 1, and also gives T0 equal to T7. Sine triangle PWM also gives the same switching sequence in one carrier cycle, but it does not give T0 equal to T7. Null vector times are not equally distributed. But when we use triangle comparison, not sine triangle comparison, but triangle comparison based PWM, in which our modulating waves were not sinusoidal, they were distorted like this. These are modified modulating waves, MR star, MY star, and MB star, which we got by adding to original modulating waves a common mode signal MCM. And that MCM was calculated by using this method, 0.5 M mid in each 30-degree interval. When we added this MCM to original modulating waves, the modified modulating waves were generated, and that gave us same switching sequence with T0 equal to T7 also, which is the case with space vector PWM. And secondly, you can see the original modulating waves are over modulated. Okay, their peak value is not 1, their peak value is 1.154. That means this technique will also give us output voltage about 15.5% higher than sine triangle PWM. Okay, because original modulating waves are they are over modulated. And as far as these modified modulating waves are, they are not over modulated. Their peak touch just 1. Their modulation index is 1. And inverter output voltage is increased by about 15.5%. This is same as in third harmonic injection PWM. In third harmonic injection PWM also, our original modulating waves were over modulated to 1.154. But our modified modulating waves had a modulation index of 1 there also, for K equal to 1 by 6, and that gave inverter output voltage 15.5% higher. But not there also T0 was not equal to T7. But for K equal to 1 by 4 in third harmonic injection PWM, T0 was exactly equal to T7, and least harmonic distortion was produced, but inverter output voltage was not as high as 15.5%. So these two features were combined in space vector PWM, and we found that these two features can be combined in triangle comparison PWM also, if instead of having sinusoidal modulating waves, our modulating waves are modified modulating waves like this, MR star, MY star, MB star, which are obtained by adding to original modulating waves the common mode signal MCM, and common mode signal is calculated like this. So therefore, it means that instead of having space vector PWM, we can have triangle comparison based PWM like this, which will give same results as space vector based PWM. That means, number one, it will give 15.5% higher inverter output voltage, higher inverter output voltage, which is also given by conventional space vector PWM technique. And secondly, it will make dual time, zero vector or null vector dual times equal, T0 equal to T7, thus give least harmonic distortion of inverter output voltage. The advantage of space vector PWM over sine triangle PWM was that space vector PWM was producing about 15.5% higher inverter output voltage, and it was giving least harmonic distortion. That is, comparing it with third harmonic injection PWM technique, it was combining K equal to 1 by 6 feature and K equal to 1 by 4 feature both in one method. Now, instead of using space vector based PWM approach, if you use triangular comparison based approach, you have to modify your modulating waves in this way by generating a common mode signal MCM, which is given by this formula, 0.5 M mid. If this common mode signal is added to original modulating waves, our modified modulating waves become like this, MR star, MY star, MB star, and it produces the same results as conventional space vector based PWM technique. That is, it produces about 15.5% inverter output voltage, higher inverter output voltage, and it gives least harmonic distortion because it divides the null vector times equally. T0 is equal to T7. So therefore, space vector PWM technique gives us these features, and we have seen that the triangle comparison method of this type also gives same results as space vector PWM, conventional space vector based PWM. So with this I will end my today's lecture. So we have seen that the space vector PWM technique can be implemented using triangle comparison method also this way, and it produces same results as space vector based PWM technique. So with this I will end my today's lecture. Inshallah, from our next lecture we will start discussing space vector based bus clamping technique. We have already discussed bus clamping technique using triangle comparison methods. We will see how we can implement bus clamping technique using space vector approach. We'll discuss space vector based bus clamping techniques, various types of bus clamping techniques based on space vector approach from next lecture onwards. Thank you. I would like to share with you some simulation results which I have simulated this triangle comparison based PWM technique at my using MATLAB Simulink software, simulation software. And these are my original modulating waves. For example, this is MR, you can see this is MY, this is MB, and this is how I have generated MCM. Okay, MCM is 0.5 M mid. And then these are my on the bottom I can show you these are my original modulating waves MR, MY, MB, and these are modified modulating waves MR star, MY star, MB star. How did I get these modified modulating waves? By adding common mode signal जो मैंने यहाँ generate की, by adding this common mode signal MCM to the original modulating waves, I got modified modulating waves MR star, MY star, MB star like this. I will share with you some simulation results. For example, these are some of the simulation results. Here you can see these are my modified modulating waves MR star, MY star, MB star. They are compared with a high frequency triangular carrier wave. Okay, we have taken a carrier ratio of 15, and these are the pole voltages. This is VRO, this is VYO, this is VBO, and these are three-phase line-to-line voltages. This is VRY, this is VYB, and this is VBR. And this is my phase voltage VRN. ये मेरी phase voltage VRN है, PWM voltage, and this is line current IR. And I will share with you harmonic spectrum of phase voltage and line current also. This is phase line voltage, and this is its harmonic spectrum. You can see what is the harmonic, what is the THD of voltage. It is just 58.5%. And this is the current, and this is its harmonic spectrum, and THD of the current is just 2.85%. It's much below than 5%. It's well below 5%, which is the upper limit of THD of the current. So these are some simulation results which I have shared with you. So you can also try to develop a simulation model in MATLAB Simulink SimPower System software, or in any other software you are well versed with, and you can generate the results, you can analyze these results. Thank you.